This is week 5 of our notes, and I want to spend a little time going over logarithms and their transformation between logarithmic form and exponential form. Logarithms and exponents are literally the same thing if we can just keep them straight in our mind. And hopefully I can show you a way that you can transform a log function to the exponential function that will be useful for you and will help you. Now this is your transformation equation. Log of base b of x equals a, where b becomes your base, a becomes your exponent, and x is the solution. So try to keep this conversion formula handy. I have even written it down on an index card and stuck it inside the front of my book sometimes, because if you're like me, this relationship is not really easy to remember, and I can get it confused if I'm not thinking straight. So whenever you're trying to do a transformation, if you start with the exponential form right here, you can actually write it in the logarithmic form once you know your a, b, and your x, or if you're given the log form, you can write it in your exponent form. All you have to do is identify your a, b, and x, and then you can make the change. For example, write log sub 10 of 1,000 equals 3 in exponential form. Let me just note that oftentimes when your log is base 10, you can actually just leave it out. So if you see this problem written as log of 1,000 equals 3, and there is no base indicated, it is always 10. It's kind of like having a power of 1. Sometimes you'll see it, sometimes you won't. But oftentimes, if you are going to use base 10 for logarithms, it will not be written. But I included it here so you could see how to find your b, x, and a. So b in this problem is the base, which is 10, x is 1,000, and a is 3. So if we want to write that in exponent form, it is going to be 10 cubed equals 1,000. Now the beautiful part about writing logs in exponential form is at this point you can check yourself for accuracy. Ask yourself, does 10 cubed equal 1,000? Well, yes, it does. But let's say you had your terms confused and you wrote it as 1,000 cubed equals 10. Well, you know that's not right. If you had 3 raised to the 1,000 power, that's not going to equal 10, and so on. So when you convert to the exponential form, you can check yourself for accuracy. So make sure that you always do that. And note, there are no logs of negative numbers no matter what the base is. So we will not be using negative numbers in this section. Now, common logs are the ones that we're talking about here, but there are also natural logs. Now, common logs have a base 10, but natural logs have a base e. So instead of having a base of a natural log, you are just going to see it written in this form. The natural log, ln of 7, is the same thing as the log base e of 7. So a natural log is just a regular log with base e. These properties that I've given you in the middle of this page are just kind of good to know. They will help you make some of your homework easier. For example, 10 raised to the log of 7 is just going to be 7. So when you raise 10 to a logarithmic power, your solution is just that number. The log 10 of 5, likewise, is just 5. E to the natural log of 7 is just 7. And the natural log of e to the 5th is just 5. So whenever you are raising those logs to a power, the results are pretty easy just to read off. Now, a moment ago I gave you that transformation formula of converting a log to an exponential formula. But now I want to give you a couple of properties of logarithms. So if you have a log raised to a power, you can actually bring that power down front as a multiplier. So log base b of x to the r is going to be the same thing as r times log base b of x. So you can bring that power down front and make it a multiplier. That'll be really handy for you in the homework. So we can use this property to help us solve problems like 2 to the x power is 20. So we don't normally have to solve for x when it is an exponent, but using logarithms we can. You will use this as we get into compounding of interest. When you have interest that is compounded continuously, you will have function x's or variables that are the exponents. So if you have a problem such as 2 to the x equals 20, you can take the natural log of both sides. So that'll give you natural log of 2x equals the natural log of 20. And now we can get that x out of the exponent by bringing it down front. And we'll have x times the natural log of 2 equals 20. Then we can divide both sides by the natural log of 2. So we will have x equals the natural log of 20 divided by the natural log of 2. And when you plug those into your calculator, you'll find that your solution is 4.32. So 2 to the 4.32 power is going to equal 20. Let's use it in an example. The approximate percentage P of his adult height that a boy will have reached at age X between 13 and 18 is given by this function. P is 16 times log of x minus 12 plus 84. So let's start by sketching the function. Just like you had in one of your earlier tests, one of the first things that we do when we're sketching these functions is to pick about 6 data points. That usually gives us a pretty good visualization of what the graph is going to look like. And in this example, since I knew we were talking about boys between the ages of 13 and 18, I just chose 13 through 19 to give me my data points. And I plugged those numbers into my formula, looking at the number of years beyond the time they are 13 to figure out what my x is. So if I'm looking at ages 13 through 19, I'm going to consider 13 minus 12 is going to give me the log of 1. So 16 log 1 plus 84 is 84. 16 log 2 of 84 is 89, and so on. So you might want to try putting these into your calculator to make sure you can get these numbers. I have gotten questions from some of you that say things like, well, when I put this into my calculator, I get something else. And everybody's calculator is a little different. That's one of the reasons I try to show all of my steps, is so that you can see exactly how to make these work. And it is good for you to try in your calculator to see what you're getting of each of these to make sure that you can get the same thing that I do, or at least very close to it. Sometimes rounding will make a little bit of difference, but see if you can get responses that are pretty close. So part A says sketch the function. The sketch will look something like that. And then part B says, what does this graph tell us about the height of a male after age 18? Well, let's count this out. That's 13, 14, 15, 16, 17, 18, 19. And what this graph tells me is that after about this level in the graph, it really is going to level out and not change by very much, which is what we can kind of expect. We think a person is pretty much at their full-grown height at age 18. So this graph confirms that after age 18, a boy is basically as tall as he's going to get, and he's not going to grow much after that age. And then it says if the boy is 5 feet at age 14, how tall will he probably be when he grows up? Well, we can put in age 5 in our graph. And we can put in 5 feet for age 14. And we know that 6 years later, from 12 to 14 12 to 14, is 2 years later. Then we can calculate how tall he will end up being. And he's at about 89% of his height at age 14. You can also read that from the graph if you wanted to look at this point. You can see you're about 89% of your height. There, you can see it right here at age 14. So if you're 5 feet at 14, then you know 0.89 of your height, your total height, is going to be 60 inches. And because that's how tall he is now. So X is going to be 60 inches divided by 0.89, which gives us 67.4. Your homework is on the next page of the lecture notes, the next 2 pages, and I want you to look at problems 1 through 5 in the homework. So please let me know if you have any questions, and I hope this video helps.